laser spot next to your source, and you correct it, and you keep it a little spot. And so, what do they find? Actually, this was work done at UCLA, led by Professor Aragats. This is about where we think the center of the galaxy is. And these are all the stars, and when they started, there's sort of a source there, and they just started mapping what they were doing. And they kept looking year after year. And notice there's nothing at the center, but all these other objects are orbiting nothing.
Where are we?
We're looking at it. We're on the we're basically at the outskirts of the galaxy, looking all the way to the center.
From the center.
Yes. Actually, this data actually was taken from Hawaii, so it's all the way from Hawaii to the center of the galaxy.
We're pretty close to the outer edges of our galaxy.
Yeah, we're about 3/4 of the way out of at the edge of our galaxy. So I'm going to show this a couple more times just because I think it's that impressive. What we have here is sort of one of the things that I was talking about. You know, we have a black hole, and how we see it as material flows into it. But what if no material is flowing into it? You're not going to be able to see it, but its gravity is still there. It's making these sources, particularly look at S02. Look, it falls, turns around, and comes back up.
How long is that orbit? I mean,
It's 15 years. If you look at it, the date is on the upper left. So right now it's 2010, that's their latest observations. It starts at 1995. So starting from there.
That's fast.
Very fast. In fact, the closest it gets to the black hole based on that positioning is 1 light day. That is, it's only 1 day's light travel time from the black hole to it. That's how close it gets to it, which is incredibly close. We're about 8 light minutes from the sun, by the way, just to give you a sense.
How fast are they going?
They're going tens of thousands of kilometers per hour. So it's orbiting incredibly. These guys are incredible. So these are some of the fastest objects in our entire galaxy. Of the 100 billion stars that makes up our galaxy. They're going incredibly fast. Why? Because there's an incredibly large amount of mass at the center of our galaxy. In fact, because just using basic physics, you can calculate how much. That mass that they're orbiting is 3.7 million times more massive than our sun.
So is that baryonic mass, or is dark matter taken into account in that at all?
That is actually baryonic mass. So for those who aren't up on this, most of the matter in the universe is actually stuff that we don't see or interact with even. It's not that it's black, it's called dark matter. It's dark, again, not because it's black. There's baryonic matter, which is us, protons, neutrons. This is baryonic. Black holes are baryonic matter. They interact in, that they must have been created from baryonic matter. That's our expectation.
Okay.
We lump them in with the regular matter, which is just in a different form now. Dark matter does not play much of a role there. In fact, there isn't much dark matter at the center of the galaxy. Most of the dark matter tends to be in the halo. In fact, there's more around our neighborhood, or there should be more around our neighborhood than at the galactic center.
And dark energy, that's a whole other
Dark
mystery.
energy is a whole other thing. Just to reiterate on the dark part, dark is more a description of our knowledge rather than anything about the material. So when we say something is dark matter, is because we don't.
Well, like 96% of the mass of the universe is dark, right?
Right.
4% is baryonic.
Yeah, about 4 to 5% is baryonic. About 20% is dark matter. So it's matter that is gravity, and then the rest of the 75% is dark energy, which is some sort of energy. And again, all that I'm saying right now, all that anybody is saying, is that we just don't understand what it is. We know it's there because of the influence it has on other sources. That is, we're not just guessing here. Their gravitational influence exists. But fundamentally, it's dark definitely comes as a description of our understanding of it. So there's radio emission that comes from our black hole at the center of our galaxy, and there's some flares which we detect in the X-rays and the infrared, but really it's not doing much. That's what we call a starving black hole. That is, there's no material falling into it, therefore there's nothing to heat up to show us that it's there. Every once in a while something falls in and it's a little bit of X-rays, maybe a little bit of infrared. But other than that, it's not doing anything. Why? We really don't understand. Because there's clearly, earlier on, there are all these stars around it that are orbiting it, and stars have winds. There's wind that comes from the sun, there's particles flowing off the sun. That material should be flowing into the black hole, not from our sun, but from the stars that are around it. We don't know. But here it is. From way back when, from starting with the time of Newton, when he was just thinking about gravity, and then people thinking about objects where you couldn't, where they were so massive that light couldn't escape, then finally to the point of it saying, hey, look, we have all of these massive objects at the centers of galaxies. There's one in the center of our galaxy. So we've come a long way in terms of understanding black holes. But at the same time, we've just gotten to the point of asking the right questions, I think, rather than understanding it. We know a lot about them. I don't want to diminish that because we've come there's been an enormous amount of understanding from the beginning till today. But at the same time, there's a lot yet to learn. And this is for objects in our own backyard. But I will close now with just talking a little bit more about Byurakan, just since it did play such a pivotal role. The Markarian Catalog is not something that's, it's basically anybody who works on active galaxies knows about Markarian galaxies. It's prevalent, there's just no, this is not just jingoism or hooray for us. This is a fundamental advancement that was done. It was motivated by Victor Hamartsunyan, who, although he did conjecture these dark masses at the centers of galaxies, his idea did not turn out to be right. These are not explosions that are coming out. This is actually accretion. It's the reverse of that. It's material flowing in, not material flowing out necessarily, that's causing all this emission. And it was the surveys that were done there that really gave us all of these Seaford galaxies and allowed us to really study the nearby versions of these and then put them all together, all these various the radio galaxies, the quasars, the Seaford galaxies, it all came together under this one idea of, hey, you've got a supermassive black hole at the center that's providing all this energy. And so, but how's Byurakan doing today after all these years? Well, it looks very nice. Victor Hamartsunyan passed away in 1996, and so his office there is in fact a museum. You can go and visit it. Are you drawn? Oh. So free on Wednesdays. I gave a talk at Byurakan a few years ago, and Edward Khachikian, he was the astronomer who came to the US in the exchange program. He's in his 80s and he's still working, and he actually still comes here once a year, and I've started collaborating with him. He's an amazing guy. He's observed that most of the great observatories in the world, and the papers that he wrote with Dan Wiedemann are really critical papers that are still being cited. Unfortunately, the 1-meter telescope which did this survey needed a renovation, and they're working on a renovation, but they've run out of money to finish that renovation. The 2.3 meter, which is just a pretty picture I can put up there, is a modern telescope. It was built in the 70s. And a telescope is great, but you need a camera to take pictures or take a spectrograph to take a spectra, and they just don't have the money for the instrumentation. But to end on a more upbeat note, this just came out a few weeks ago. They have struck a deal with the Italian government, it looks like, hopefully this will come through, for 250,000 euros for an exchange program between Armenian astronomers and Italian astronomers, but more importantly is to have, from the French Haute-Provence Observatory, there's a spectrograph, which splits up the light of whatever you're looking at, to be brought to Byurakan to be put on the 2-meter telescope, which means now it will have an instrument to use that mirror with. Telescope is a mirror, it's very useful, but you need something else. You need to collect that light and keep the light. It used to be photographic plates. That's long gone now. Now it's all electronic detectors, just like your digital camera, and you need that. And to be competitive on the world astronomy stage, you need good instrumentation. And that's where they're at. I'm hoping that it will succeed. Dr. Hamartsunyan was very nice to me when we were there, and he seems to have at least made a good deal for Byurakan for it to continue, because admittedly, astronomy is not the greatest concern of the post-Soviet